there's another problem for your homework that seemed to be providing quite a bit of difficulty, so I thought I would talk about it briefly. There's a problem where you have a ramp like this, and it tells you that it's up some angle theta, and that there's a mass, some mass m here, and it tells you its initial velocity at this point. I don't know exactly what it is. It could be some numerical value. And it tells you, I think the information that it gives you is the distance that it travels here. So it gives you this displacement, we'll just call that d, maybe d1, and then it also tells you this displacement over here is d2. Basically what happens is there's a frictional force that acts on the block as it slides down the ramp, and the same frictional force, well, sorry, not the same frictional force, but the coefficient of friction between the block and the ramp here and the coefficient of kinetic friction between the block and the ramp in this stretch are the same. Now, the frictional force that we need to worry about in both these cases might be slightly different. So the frictional force on the ramp is going to be equal to the coefficient of kinetic friction times the normal force on the ramp. Whereas the frictional force while it's lying flat is going to be equal to the same coefficient of kinetic friction times the normal force on the flat part. And if you can remember when we talked about how these compare, they're going to be slightly different. It's not simply equal to the weight in both cases. It is equal to the weight during the flat part because of Newton's second law in this direction must equal 0. The way that we figure that out on the ramp is because the Newton's second law at along a direction that is perpendicular to the surface here also is equal to 0. And so the normal force here has another function. I think it's a cosine of theta times the weight. But the way that we calculate all this information, we're told how far it travels until it stops here. We're told how far it travels until it stops here. And it really comes down to writing several expressions. This is a review problem to some extent, and so there are probably a couple of ways that we might be able to solve this problem. The way that I thought would make a lot of sense would be to write Newton's second law while it's on the ramp, and then Newton's second law when it's flat. So when we do that, the acceleration for these two things are different. The mass is still the same mass, so those are going to be the same. Now the net forces here, when it's on the ramp, are going to be different than when it's on the flat portion. On the ramp portion, the two forces that are acting on this are the force that is acting down some component of the weight. So we have our weight, the force due to gravity, acting on this block going straight down. It has a component along the surface here and also a component perpendicular to that. There's also a normal force pushing out. All right? So here's the normal force, and this normal force is equal and opposite of this component of the weight, which is perpendicular to the surface, and we have the frictional force, which is going back up, and that depends on the coefficient of kinetic friction. The coefficient of kinetic friction and the normal force on the ramp, right? So we can write that expression down here. At least we can write this. The most interesting one is to write it for along the direction of the ramp, and so that's going to be whatever the component of this gravitational force is along the ramp minus the frictional force going back up, equal to mass times acceleration. Now we don't know exactly what that acceleration is, but we do know what the weight is, and so we have a lot of things that we do know about this particular expression. But the one thing we don't know is the acceleration, and the other thing we don't know is the coefficient of kinetic friction. Then when we write the Newton's second law for when the block is in the flat portion here, what we can do is determine the net force acting on it, which is only going to be due to the frictional force, so the frictional force here is going to be equal to mass times the acceleration, so that tells us the acceleration here is going to be negative, obviously, and it moves until it goes to a stopping point. So again, this is the mu k times the normal force in the flat section. So what's that leave us with? We have a couple of expressions and a couple of unknowns. So this expression here is really mu k times the normal force during the flat portion equal to the mass times the acceleration during the flat portion. Up here we have That expression is going to look like this. Let's see if I can write this out and still be legible. Is going to be the weight down, which is mg sine theta, minus mg cosine theta times mu k, right? Because this is that normal force component. And that's going to be equal to mass times the acceleration on the ramp. Make sure these are two separate things, right? These aren't the same thing. So here's when it's on the ramp, and here's when it's on the flat part. I think this is correct, but if I make a small mistake, you're accountable for making sure you figure out what that is. But now, what do we don't know? We don't know what the acceleration is here, we don't know what the coefficient is here, we don't know what the coefficient is, and we don't know what the acceleration is. Well, these are the same, so that gives us two equations and two unknowns. But how do we find each of these unknowns? That might be a little bit tricky. We're told what the initial velocity is here. We don't know what the velocity is at this point, but we do know what the velocity is when it stops moving. We know that the final velocity over here is equal to 0 meters per second. We know that the velocity inside here is kind of the final velocity for the point where the block is coming down the ramp, but it's also the initial velocity for when we consider the block moving along this flat portion. So if we can write a kinematics expression that relates the change in the velocity, that relates velocity to the distance that it travels, right? Something like vf squared equals vi squared plus 2as, let's say, where s is the displacement. Well, we know what the displacement is along this ramp. We know what the initial velocity is. We were told what that was. We can figure out what the final velocity is, at least we can relate that to something else. So this expression, if we use this part for the ramp, so this is the initial velocity on the ramp, and this is the final velocity on the ramp, and this is the acceleration on the ramp, and this is the displacement on the ramp. We can write a fourth expression. You're probably getting nauseated by this. A fourth expression, which is the exact same as this. The final velocity on the flat portion squared equal to the initial velocity on the flat portion squared, plus 2 times the acceleration on the flat portion times s on the flat portion. And we know what s on the flat portion is. That's what I labeled up here as d2. It gives us the acceleration in the flat portion. We know that the initial velocity in the flat portion was the final velocity for the ramp portion, and we know that the final velocity for the flat portion happens to be equal to 0. So what's that tell us? So this is equal to 0, and then this value equals this value, right? The final velocity for the ramp is equal to the initial velocity of the flat part. So these things that gives us one unknown which we can solve for. We know what this is, we know what this is, we know what this is, and here are these two other unknowns that we needed from these expressions up there. Right? So it seems crazy, but you can actually figure out what this stuff is. And this is at least one way that I think you can solve this problem. There are probably others, so I would encourage you to check some of those out.